Hello, grade 12s. Welcome back to the channel, Science Therapy, hosted by the one and only science therapist, Abutewa Sos Ugobela Maths. And without any further ado, let's look at these questions that we have here. Okay, so we have question 5. It says a group of learners used the reaction between magnesium and hydrochloric acid to measure the average rate at which hydrogen gas is produced. They add 10 centimeter cube of 1 mole per dm cube of hydrochloric acid, and then to what? To 0.048 gram of magnesium powder in an Erlenmeyer flask at 20 degrees Celsius. The balanced equation for the reaction is as given there. Okay, so we have our balanced equation right here. And then they say the learners' experimental results were plotted on graph A, right? Then, okay, 5.1 says define the term reaction rate. So how do we define reaction rate? We say reaction rate is the change in the concentration of the products or reactants per unit time. Right. So there we go. That's our definition for 2 marks. Then 5.2 says calculate the volume of hydrogen gas produced in the first minute. In the what? First minute. If the average rate of production of hydrogen gas is 0.67 centimeter cube, right? So now the first minute obviously means that the first 60 seconds. So as we can see, our time here is given in seconds, and we know that 1 minute is equivalent to what? 60 seconds. So that means we are looking from 0 all the way to 60 seconds here. So that means the volume that we are trying to calculate here is the volume that will be represented over here. But as we can see here, we don't have any values to be able to read it from the graph. So that means we would have to do what? Calculate, as they said. Then 5.2, we are going to say rate of reaction is equals to change in volume over change in time. As we can see that our rate of reaction has been measured volume per unit time, right? Volume per second. So rate of reaction is equals to what? 0.67. And then to get our change in volume, that's the volume finally, which is V. And then what's the volume initially? That would be 0. And then what's the time finally? That's 60 seconds. And initial time is again 0. Then if we can just write this in fraction form, that would be 0.67 over 1. Then we obviously need to cross multiply here. So this is V minus 0 is V. V multiplied by 1 is V. And then we have 0.67 multiplied by 60. And then of which when you multiply there, you are going to get what? You are going to get 40.2 centimeter cube, right? So since we are dealing with centimeter cubes there, we might just as well leave it like that. So, okay, 3 marks, formula substitution into the formula, and the correct answer with the correct SI unit.
We're enjoying ourselves here.
Right. So that's how you would approach that one there. Now, 5.3 says what? So let's erase here. 5.3 says how long in seconds does the reaction take to run to completion? Give a reason for the answer by referring to the gradient of the graph. Now we can see that our graph here is increasing sharply, and then all the way from 0 to let's say 30 seconds. And then here, the reaction rate, as we can see, it's starting to decrease all the way like that. And then decrease up until it gets to 120 seconds. Now we can see after 120 seconds, our graph is becoming horizontal. And from our maths, we know that if we can just draw tangent lines here, and then we can see that our tangent line is becoming horizontal, meaning it's now parallel to the x-axis. it means that the gradient of that particular line would have to be equal to 0. But then according to rate of reaction, if the gradient of the graph becomes 0, it simply means that the reaction has run to completion, right? So in 5.3, we are going to say that means that the reaction actually stops at 120 seconds, because after 120 seconds, that's where now the graph starts to become horizontal. That's where the gradient of the graph is now equal to 0. So we are going to say it's at 120 seconds, 120 seconds. And then we say the graph, or the gradient of the graph is equal to 0 after 120 seconds, right? So after 120 seconds, the gradient of the graph equals to 0. Okay, so that's how we were supposed to tackle that one right there. Okay, now let's go to 5.4. 5.4 says calculate the mass of the reactant left in the flask when the reaction is complete. Note that it doesn't say the mass of the reactants. It says the mass of the reactant. So that means there's only one reactant that is left. Now this goes back to what? This goes back to our grade 11 stoichiometry, where obviously we understand that we need to calculate the limiting and the excess reagent. So in order to know which reactant is left, remember the reactant left is basically talking about the what? The excess reagent. So that means we are looking for the mass of the excess reagent. Yes, how do we write reagent? Okay, there we go. Excess reagent. Right. So, okay, now what we can do is to first calculate the number of moles. So you still remember the steps to calculating limiting and excess reagent. So if we can just recap on that. So basically we used to say step number 1 is to first calculate the number of moles. Calculate the number of moles of each compound, right? Of each compound or molecule. So starting with our magnesium here, we can say, let's calculate the number of magnesium, right? Note that the number of moles that we are calculating on our first step is the available number of moles. So let me indicate a number of moles of magnesium available. So in the beginning of the reaction, and then this is mass over the molar mass. So we are choosing this formula specifically because we are given the mass of magnesium powder, and then we can calculate we can get the molar mass from the periodic table that we have right here. And then this is 0.048. And then our molar mass is what? 24, right? As we can see right there. So 24. Then you're going to grab your calculator, 0.048 divided by 24. So your calculator will give you 0.002 mole. If you have it in normal, if you have it in scientific, that's 2 times 10 to the exponent of -3 mole. So both of these answers are correct. They represent one and the same thing. Right, and then now we have to calculate the number of moles available for hydrochloric acid. So note, this is the one available. So how would we calculate this one? Now, looking at this, we can see we are given the volume and also the concentration. Remember, the formula to calculate the number of moles has to be chosen based on the information that you have, right? So you don't just calculate using this one. For this one, we can see that hydrochloric acid, we are given the volume and we are also given the concentration. It wouldn't make sense for us to use this formula. So we have to use which formula? N is equals to C multiplied by V, where our concentration, C multiplied by V, our concentration is 1, but then we have to take note of one thing. If we are substituting the volume into this formula here, we need to make sure that the volume is in decimeter cube, right? So to convert centimeter cube to dm cube, we need to divide by what? 1000. So to get our answer in cubic decimeters, we have to say 10 divided by 1,000. And then we get 10 divided by 1,000. That's equals to 0.01 cubic decimeters. Right. Then you put it here, 0.01. So 1 multiplied by 0.01, that's 0.01 mole. So now you have the number of moles available for each of these reactants. Step number 2, if you can still remember, is to compare the molar ratio, right? To find, compare molar ratio to find excess or limiting reagent, right? So this is where now we are calculating the number of moles required, right, by the use of ratios. If we can say this is magnesium to what? To hydrochloric acid. Having to check here, what is the ratio of reaction between magnesium and hydrochloric acid? So the ratio here suggests that for every 1 mole of magnesium that will be reacted, we need to have 2 moles of hydrochloric acid that is being reacted, right? So if we are to react, let's use our magnesium as the reference. If we are to react all of this, right? If we are to react all of the magnesium here, how much of the hydrochloric acid would actually be needed to react with all of that magnesium? So it means we have to do this. We have to put all of the magnesium here and say how much of the hydrochloric acid is needed. So X. So now if we cross multiply here, obviously this will give us 2 multiplied by 0.002, which will give us X is equals to 0.004 mole. So that means of hydrochloric acid. That means the required number of moles of hydrochloric acid is only 0.004, right? We only require to react 0.004 mole of the hydrochloric acid in order to react with all of the magnesium. So all of the magnesium will be reacted with, right? All of the magnesium will come to completion while there is still some hydrochloric acid left. So how do we know that there will be some of the hydrochloric acid left? Because the number of moles required is actually less than the number of moles available.
I can see what they're doing, what it's doing. I can see it, I feel it. It's cooking.
Remember, if the number of moles required is smaller than the number of moles available, we say that particular substance, so substance is in excess. So that particular substance is in excess. That means, in other words, we can then conclude here that our hydrochloric acid is in excess. And then which obviously means that magnesium here is a what? Limiting reagent. But are we done by just concluding that? No, right? Remember, the question is saying we must calculate the mass of the reactant left. Okay, so now we can see that we only require 0.004 mole to react with all of the magnesium. But then we have 0.01 mole available. So if we only require this out of that, how much will be left? How many number of moles of the hydrochloric acid will be left? So this is the next question that we are trying to answer here. Okay, so which means this is what we're going to do now, right? So we are going to say to then calculate the number of moles of hydrochloric acid in excess. We need to say the number of moles initially available, which is 0.01, minus the one that's required, or the ones that will react, 0.004. You grab your calculator because decimals can be a little bit crazy, so you don't want to play around with this. So that minus that gives you 0.006 mole. I bet if you wanted to do it with your mind, you wouldn't have thought of that. So decimals work in different ways. So 0.01 minus 0.004, you get 0.006 mole. But then remember, we are not looking for the number of moles in excess. We are looking for the mass in excess. So we can say, let's use the number of moles in excess to then calculate the mass. So the mass will be N multiplied by the molar mass. so which will be 0.006 multiplied by the molar mass of hydrochloric acid. So molar mass of hydrochloric acid, hydrogen is what? 1 mole. And then chlorine is waste chlorine. There we go, 35.5. So 35.5. Make sure that you are using this periodic table that you get from your answer sheet, right? So even when you are practicing, do not use some of the periodic tables that you get from your textbooks, because those ones you find that they're not rounded off, right? So make sure that you practice with the one on your question paper. You can just download it and print it out, right? So that you always get to practice things that will be in the exam. So because if you are used to the values in your textbook, sometimes you might substitute the values from your textbook when you are about to write an exam, and that will cost you marks. So make sure that if you are preparing for the exam, you practice with exam questions. So 0.006 multiplied by 36.5. So this will give us 0.219 gram, right? And there you go, 7 marks just like that. So yes, it was a pretty long question, but then just needed you to understand your concepts from grade 11, limiting and excess reagents, and then that's your basic stoichiometry right there. So I did mention it a couple of times that when it comes to these topics, this topic here specifically, you will need to know your stoichiometry in order to survive it. In fact, question 5, 6, 7, you would have to know your stoichiometry in order to survive those questions. So make sure that you go back to your grade 11 and revise your stoichiometric calculations. Right.
Hey, he's not make sure. He's not make sure. He's a full case.
Let's now go to 5.5. It says when the concentration of hydrochloric acid is increased, the learners observe that the rate of reaction increases as well. Use the collusion theory to explain this observation. So this is only 2 marks. Usually you find it's 3 or 4 marks. So, but then what I'm going to do here is I will try to give a full explanation for all of this, right? Where it's 2 marks, but then I prefer to just write everything in full so that you understand how this collusion theory questions should actually be explained, right? So the first thing here, we are dealing with what? Concentration. It's an increase in concentration. So your opening statement should be this: increasing the concentration, increasing the concentration increases the number of particles. The number of particles per unit volume. Per unit volume. So that's point number 1. Then point number 2, you will say more particles. So you will say more particles collide with correct orientation. So very important for you to mention that. So remember, when we are marking here, we are looking for keywords. More particles collide with correct orientation, and then more effective collisions. More effective collisions per unit time. Per unit time. And then more effective collisions per unit time. Thus, the rate of reaction increases. Thus, the rate of reaction increases. Right. So that's basically how we go about answering those questions there. Right. So make sure that you write the full explanation, and then they're just going to come and mark the ones that they actually want. Right. So according to your memo, I know that they would be marking you having to mention that there will be particles that collide with correct orientation, and also mentioning that more effective collisions per unit time, right? But then it's important that you lay down the explanation properly so that your marks are not disputed.
Wetin be this? Wetin be this? Jesus.
Then, okay, 5.6. In another experiment, the magnesium powder is replaced with an equal amount of zinc powder. Redraw the graph provided in your answer book and sketch on the same axis the graph that would be obtained when the zinc powder is used. So, okay, let's understand this. Now, this is on nature of the reactant, right? So magnesium and zinc, they would be both reactants, right? So this is on the nature of the reactant. We have to understand what's the nature of magnesium, what's the nature of zinc, right? Now, from our reactivity, grade 10, you used to talk about the reactivity of the elements. You will understand that the reactivity of the elements increases from the right going all the way to the left of the periodic table, right? So this is in the order of increasing reactivity. So this is increasing reactivity of metals. So if we can check here, we can see that our zinc, where is zinc? Zinc is right here, and then magnesium is over there. Now, given the fact that the reactivity of metals increases from the right to the left, it would make sense that magnesium here has a higher reactivity than zinc. And therefore, since magnesium has a higher reactivity, it means that it would be the one that produces what? A higher reaction rate, right? Or a faster reaction rate. While zinc here would produce a lower reaction rate or a slower reaction rate, right? So having to redraw here, that means this is how I will indicate this. I have my graph here. So remember, it's just a sketch. We are not really focused on the values. So let's first indicate the original one, graph A, which is for magnesium, right? So that is graph A. And then graph B, representing zinc, will be like this. So since it has a lower reaction rate, that means it will be like this. So note that the value in which the reaction comes to completion, which is the volume of hydrogen gas produced, will still be the same. Because remember, increasing the rate of reaction or lowering the rate of reaction does not necessarily decrease or increase the products that will be formed, right? So it's just a matter of graph A will just reach completion much faster than graph B, right? But then basically, all of these two graphs here will produce the same volume of hydrogen gas, right? So it's just a matter that one will be much faster in doing it, and then the other one will be slower. So I'm trying to curve it nicely here.
What are you saying? What are you saying? What is he saying?
Whoa. Okay, but then yes, you get the idea. So where there will be constant, they will all be constant at the same value here. So this is the volume of H2 gas in centimeter cube, and then obviously this is time in seconds, right? This is time in seconds. And then your graph A will basically look like that. Your graph will just look like that. Okay, right, yes. So that's basically how you are supposed to tackle this question here. So indicate here this is graph A, and then indicate this is graph B. So graph A and graph B right there. Okay, so that's how you are supposed to tackle that question. Make sure that you come back to this video, watch it as many times as possible, and try to understand the approach that I took into answering these questions here. But then with all that being said, please press that like button, press that subscribe button, and then also share the link with your friends and classmates so that they may also find assistance. Remember, do not be selfish. We are winning as a team.